Swayam Prabha. Digital India. Educated India.
Good evening. So today we'll start with introduction to the PyTorch. So let us see what we will see today, and subsequent classes we will see more of PyTorch. But today we will start with some introduction to this framework. So this framework is one open source machine learning library, and there are other libraries as well. But it was developed by Facebook's AI research lab, and it became very, very popular. And nowadays, it is very, very popular in the community of researchers as well as developers. Now, why it is so popular? It leverages the power of GPUs. Basically, it is very, very GPU friendly, and programming is seamless, and automatic computation of gradients. So when you have gone through the DNNs, so you can see that you need the most important step for training one neural network is computing the gradients. And in this framework, the computation of gradients are very easy. It's just one line of code. So we will see that. And of course, the structure of PyTorch is very, very Pythonic in nature, and the development is very, very easy. So it makes it easier to test, develop your new ideas. Basically, if you are developing your own neural network or own machine learning algorithms, it's very, very easy to adapt steps and implement your ideas and do experiments, tune the parameters, and also easy to test as well, right? So we'll see all of these flexibilities while using the PyTorch. And so let's go forward with the other libraries. So what are the other libraries available instead of PyTorch? We have CNTK from Microsoft. Cafe is there. Cafe 2, one updated version is there. TensorFlow 2 is there. Keras, Theano. So all these frameworks are also available, which does pretty much the same job as PyTorch, we will see. So it depends on the developer's choice which framework to go with. And at the end of this course, we will at least see 2 of these frameworks, so PyTorch and TensorFlow. And you will see the usage of these 2 frameworks and how to accelerate your deep neural network trainings mostly, and how to do that in both the frameworks that we will see. So the tensors are the most important data structures in PyTorch. So while you have arrays in NumPy, where you can actually represent a set of data, in PyTorch you have tensors. And why the tensors are most important in PyTorch? Because they can also be used in GPUs. And arrays cannot be directly used in GPUs. Rather, tensors in PyTorch, which is the data structure we are talking about, can be easily adapted into GPU computation, and which will give you or provide you the faster computation or faster training of the neural networks that we'll see. So talking about these frameworks, we will just first let's discuss about the random matrix that you can have in PyTorch tensor, right? So let's say I want to use PyTorch, so you just use import torch. Torch library will be imported as torch itself. And then let's say I want to define one matrix, 2x3 matrix, which is essentially one tensor. So sorry, x is equal to torch dot rand. So a random 2x3 matrix will be generated, which will be used as tensor. So x is a tensor of 2x3 dimension. Okay, so 2 dimension it has. One is 2 and another is the size of another dimension is 3. Let's say I have defined another tensor y, which is torch dot rand function. So rand function is essentially used to give you random values in the tensors, which will be defined in these shapes and sizes, right? So the shape is here uh, uh, two-dimensional, and you have 3 cross 3, okay, as the size of this y tensor. You can just print x and y just to see the values you have generated. Now, if you want to introduce, or if you want to initialize one tensor with all the 0 values, so becomes very important for several machine learning and deep learning algorithms to generate a set of random zeros, and the number of zeros you can define in the argument. But let's say how we can define such tensors. So torch dot zeros will give you a set of zeros. Now how many? The dimension will be defined in these arguments. So two-dimensional tensor that we are defining here as x with 5 in first dimension, 5 elements, and 3 is the second dimension's size. Now, if you have already one data, so let's say 5.5 and 3, you have this data already, and you want to convert it into a tensor. So this is essentially one numpy array, and you want to convert it into a tensor. So torch.tensor method or function will give you the converted tensor from the existing data that you have. So this function is very handy when you have already a data set present and you want to convert it into a tensor, so that you will use that for your GPUs that are available at your disposal. Now, to know the sizes of the tensors are very important, because while designing your algorithm, while you are working with large tensors, so at times you need to get the sizes of different tensors that you are defining. And in that case, dot size function will give you the sizes of these tensors. So x dot size will give you the size of the tensor. Now, different operations you can define on the tensors, like adding the tensors, indexing the tensors. So all these are operations, basic operations that you will do while designing your algorithm, basically machine learning and deep learning algorithms in PyTorch. So x and y here are two tensors we are defining. One is 4 cross 4 random tensor, and another is 4 cross 4 random tensor as y. So x and y two tensors. If we want to add, torch.add function will add these two tensors. And remember here, while adding, so while operating on the tensors, any operations you are applying, you need to know whether the sizes are compatible or not. So if the sizes are not compatible, then it will return one error. So here, as you can see, x and y, these two tensors having 4 by 4 and 4 by 4, these two are compatible to add, and it can be added. Now, indexing is very essential tool to actually get access to several elements depending on the start and stop of your indexes. Okay. So this is very similar to your NumPy arrays. So indexing, slicing, whatever you say, it is same as the array slicing or array indexing that you use for your NumPy arrays, and you can directly use slicing on the tensors as well with the same concept. You can also resize the tensors, and if you want to resize or reshape the tensors, so let's say we have one random tensor as x 4 by 4, and we want to resize it to, let's say, 1 dimension. So this is a 2-dimensional tensor that we have defined as x. Now y is equal to x dot view. So view function is used to resize your tensor. So here total 16 elements were there in that 2-dimensional tensor, Now we have one-dimensional tensor where we have 16 elements. So Vue has actually flattened that two-dimensional tensor into one-dimensional tensor. So this Vue function will be very, very useful while you are working with neural networks, uh, be it artificial neural networks or convolutional neural networks. You will be using Vue function very, very randomly. Now, you can also use this -1 in as your one argument in your dimensions. So what does this do? This also comes very handy when you are working with dynamic dimensions. So let's say you are working with one neural network training where you need to define your number of batches or maybe number of dimensions that you are using for your input data. So if your input data dimensions or let's say number of batches vary, so you cannot hard code the resizing factors. So let's say I want to resize this X tensor into another two-dimensional tensor as Z. Okay. So X is one two-dimensional tensor, 4 by 4. Now I want to resize it into another two-dimensional tensor as Z. Now, x.view function I will call, but here I will not hardcode the first dimension, let's say. I want to hardcode only the second dimension. So in the second dimension, I want 8 as the size. And the first dimension, I want it to auto-calculate and reshape it automatically. And that's when we will use -1 as the argument. So it will automatically, when you will print the x.size and y.size and z.size, you can see the torch size for x is 4 by 4, torch size for y is 16, and torch size for z is your 2, 8. So basically, 2 is automatically calculated. So this is a very simple example, but when you are working with multidimensional tensors, let's say 4-dimensional or 8-dimensional tensors, then figuring out one dimension with randomly or dynamically varying input sizes, it is very, very handy. Now, let's say you have one tensor here, 4-dimensional tensor, as I was mentioning, where X is randomly initiated 4-dimensional tensor, where we have 1, 4, 32, and 24 as dimension sizes for 1, 2, 3, 4. And you want to resize it. Let's say first dimension you want to keep it as 8, second dimension you want to keep it as 2, and third dimension you don't know because let's say your input is varying for different dimensions, and third and fourth dimension you want to keep it as 3 and 8. So what will be the third dimension? So it will automatically be calculated depending on the values you are getting as input tensors, and it will be automatically revised and added. So here, if you want to print the y.size, then you will get what the output should. So try it out, and you will see what the output you are getting, whether you are calculating it perfectly or not. Now, there are tensors and there are arrays. So as I was mentioning that NumPy, which is very, very basic library that Python uses for, let's say, array and list data structures, mostly they are designed for your CPUs. And while we were working with tensors, this is designed for your GPUs. So you need to know the difference between these two. But the scope of tensors is not only confined to your GPUs. You can run also the tensors into your CPUs as well. So that we will see in this session as well, how we can run both in CPU and GPUs. Now, let's say I have one tensor here for randomly sequence. So here we are initiating one tensor with 5 ones, and this is the value of A, which is one tensor with 5 ones, as you can see. Now B is one NumPy array. I want to convert the tensor into one NumPy array. So you can go in both the dimensions or both the realm of array and tensors by using this simple conversion. So if you want to go from tensor to array, a.numpy will actually convert your tensors into your array or NumPy arrays. And if you have, let's say, I have one NumPy array, which is set of ones, a equal to NumPy dot ones 5. So as you can see that the PyTorch, Torch, tensors, and NumPy arrays are almost similar in structure or definition. So that is why it is very popular. Now, as you can see here, I have one set of NumPy array. Now I want to convert it into tensor. So from NumPy, from underscore NumPy function will transform your array into the tensors. So if you have already data available as array elements in your program, then you can convert it into tensors using this simple function. And you can leverage the flexibility of available GPUs to run this. Okay. Now I will talk about matrix multiplication in PyTorch, which is very fundamental, basic, and very useful and widely used operation in AI applications. So first we will just import the torch library. So we are defining or initiating two matrices. So mat1, the first matrix having 2 by 3 elements with random values. Second matrix, we are having 3 cross 3 as the random values. So as you can see, when we are trying to matrix multiply these two, we need to be again compatible for multiplication. So you cannot multiply 2 cross, let's say 4 and 3 cross 3 matrix, right? So uh, the columns and the rows for these two matrices need to be same, and that's when you can do or apply this .mm function to multiply these two matrices. And this matrix multiplication is on the tensors, not on the arrays. So this matrix multiplication, you can actually do it, or you can use GPUs to do this matrix multiplication. But usually we do not do, and you can check the size of this result, and the size of the result will be 2 by 3 because you are multiplying 2 by 3 into 3 by 3 matrix. So your resultant matrix will be 2 by 3. Now, we do mostly the batch matrix multiplication. So when you are working with machine learning applications, you don't do single matrix multiplication, right? So batch matrix multiplication is widely used mostly, and for that we need BMM function to apply on the batches. Now, how we will define batch matrices? So let's say batch one is we want to define one batch matrix. So the first dimension is basically the batch size. So 10 is the batch size. That means 10 samples with this spatial structure. What is the spatial structure? 3 by 4. So 10 3 by 4 matrices you have, and another 10 4 by 5 matrices you have as batch 2, and you want to multiply these two batches, batch 1 and batch 2, BMM function batch 1 and batch 2. And if you want to see the resultant batch matrix size, now the size will be 10 because 10 matrices you have multiplied with 10 other matrices, so resultant you will get 10 matrices. So 10 samples, resultant 10 samples you will get 3 by 4, 4 by 5 you have done the matrix multiplication for, so you'll get 3 by 5 as the resultant matrix dimension. Apart from batch matrix multiplication, there are other operations also which are very important for your AI applications, like concatenation. So you can concatenate two tensors. You can actually squeeze or unsqueeze two tensors. So let's say you want to reduce the dimension of one tensor, let's say from 4-dimensional to your 2-dimensional tensors you want to squeeze. You want to then use squeeze function. You want to increase the dimension, you will use unsqueeze function, and so on and so forth. So for each definition of these functions, you can go to pytorch.org docs master torch.html tensors. So here you can define, get the definition of each functions or each operations that you can apply on the tensors and their descriptions and their usage with examples. Now, while working with neural networks, mostly from the deep neural networks perspective, computational graphs are very, very important. So computation graphs are essentially the graphs which defines the neural network operation. So here X is input tensor, W is your input weights. So these are the parameters you want to get the value after training this neural network from, and B is the bias. So so let's say these three are the input to your neural network. So I hope you have revised the neural network concept to understand the computational graphs. Now A is, so essentially what you are doing here is that X into W plus B is your output tensor, right? So so this is a linear operation you are doing. So W into X plus B, and W is your parameter set or parameter tensor that you want to get the value from the training. So how you do the training? Once you have the prediction as the output here, Y, and once you have the ground truth, let's say Y dash, then you compute the loss, and depending on the loss, you compute the gradients with back propagation, and then you update the weights and biases with these gradient values, and then again you do the forward pass. So once you do the flow complete from XWB to Y, that is called one forward pass, right? So to define this forward process in PyTorch, let's say we have X as our input tensor. So one input tensor we are defining as 2 by 2 as all ones. So basically this is, we are initiating the values. For your training, you will get the values from your inputs. Now we have Y as the outputs. So this is also we are initializing as 2 by 1. Okay. And now the value for the parameters, we are defining it as torch.rand with 2 by 1, and we are initiating the coerce underscore grad this flag to true. So once you have defined the neural network, or you want to go to define the neural network, you need to know which are the input variables or input tensors and which are the parameter tensors or weight tensors. So basically W and B are the parameters which you want to update with each training iteration, and at the end when you have minimized the loss, then you will get the finalized W and B values, right? And that is your target. So that means with you want to compute the gradients for these parameters. So W and B parameters you want to compute the gradients. So requires grad equal to true. So this flag will let the PyTorch framework know that W and B are the parameters that we are working with. And when we will compute the gradients, these parameters will get updated, not X and Y, because by default requires grad is false. And we did not define the true flag here for X and Y, which is the input and output tensor, right? So once we have the computational graph defined, so basically here P is the prediction of the output, and as you can see, X into W, we were doing it matrix multiplication plus B. So this is the linear operation that we are doing, and then we are applying the sigmoid function. So sigmoid function is essentially the nonlinear function you want to apply onto your output of the linear function, and then you are applying this prediction for computing your loss, right? So this is the P that you are interested in computing, right? And then you compute the loss. So which is, let's say here we are trying to compute the cross entropy loss, which is minus y into, so this is the positive class and this is the negative class prediction. So this is the loss. Basically, you won't use any formula for that. You have already library functions that are available to compute the losses. So we will see such use of the loss functions with just calling the function. Here we are defining the function to compute the loss. And then once you have computed the loss for, let's say, many losses, you just compute the mean or average for all the losses, which is the cost. And once the cost is defined, then you are trying to minimize the cost function or cost value to get the prediction more concrete, right? So that means with your gradient computation, you will update the parameters which you have defined as W and B, and then you will actually use or compute the gradients and update those parameters using what that you will see now. So first we have computed the predictions, then the loss, and with this cost, just calling this backward function will compute the gradients automatically. And computing the gradients is the most complex function or complex steps for training one neural network. So how we are training the neural network? We have one set of input tensors, a set of weights and biases. So basically the parameters. So parameters we are combining with combining the weights and biases together. We have parameters. And then we are applying this linear function, the nonlinear function. Then we are computing the loss with the ground truth. And then we are computing this backward pass, which is essentially computing the gradients. So this backward pass will actually run your back propagation and compute the gradients with respect to all the parameters that we have defined required grad equal to true. Now, if you want to see what are the gradients for each parameter, you can print w.grad and b.grad to see the gradients. So, in a nutshell, what are the training procedure? So, so that we will use PyTorch functionalities to define the training of neural networks. So, and of course, when you will define deep neural networks, that means when number of layers. So this, whatever we have seen as the computational graph so far, that is just the one layer. And if you have deep neural networks, that means the number of layers will be increased, and you might have also convolutional neural networks where several of these layers will be convolutional operation. So convolutional operation also inherently uses matrix multiplication because you can represent your convolution operation as matrix multiplication. And that is why batch matrix multiplication is very, very important, because all these deep neural networks that we will train, that will use batch data. So let's define the training procedure. So each step here you can see, define first the neural network, then iterate over the data set of the inputs. So this is very, very important step where you get or prepare the data, and then you iterate over the data set to feed to this model that you have defined in this first step, because this neural network model will take all the training data set that you have processed, and it will actually train your neural network and update the parameters until or unless you get the desired accuracy. So then what the step is, the process of the input through the network, then computing the loss. So computing the loss, we have seen how to compute the loss, but with respect to predefined functions, how we will compute the loss and how we'll define it inside a PyTorch framework, specifically, that we'll see in the next. And then once the loss is computed, then you can propagate the gradients back into your network parameters to update them. And last step is that to update the weights of the network. So this is just the one step of the entire training process of your deep neural network. And you will continue this step until or unless you get the desired accuracy or predefined number of steps that you want to have.